Hey everyone, welcome back to our discussion of section 4.6, Applied Optimization. This video will consist almost exclusively of examples, so if you need to review any of the material, please go back to the previous video or any of the videos from previous sections. In the last video, I reminded you about the first and second derivative tests and then never really used them. I will be using them in this video, so make sure you review those theorems before you go on. So let's jump right into it. Our first example is going to be about building a box. If we read the question carefully, we see that the box needs to have a fixed volume of 32,000 cubic centimeters to minimize the materials we need to make this box. In actuality, if you were making this box, you can think of this as minimizing the cost of making this box, which is actually our next example, but keep that in mind. To help us out, I've already drawn a picture of the box, but in general, you would have to start the problem by drawing the picture yourself. As per usual, I invite you to try this problem for yourself by pausing the video and then resuming when you're ready to work through the problem together. In addition, you may have noticed these problems are longer than the ones we've done in previous sections. One strategy you may consider using while watching this video is to break the problem down into its individual parts and do one part at a time before watching that part of the solution. This method will help you catch errors that you make early on so you don't spend too much time working with the wrong equations. Also, it might help you get the next step and then allow you to continue and do the majority of the problem on your own. For example, you may start by trying to identify an equation for the quantity you're trying to optimize, and then try to write down equations for the constraint or constraints that are involved with this problem. Then you can resume the video, watch that part of the solution, and then pause it again to try the next step on your own. Okay, so before we begin, I want to point out one major feature of this problem. We are making a box, but specifically we're making a box that does not have a top. This is very similar to the pen we built in the last example. We had to build only 3 sides of the fence. First, we should start by identifying the quantity we want to optimize. If we read carefully, we see that we want to minimize the amount of material used. This is sort of related to the surface area of the box, but we need to modify the formula to not include the top of the box. That means we have 2 sides of area h times w, 2 sides of area L times h, and only 1 side of area L times w. Here we see the first major difference from the previous 2 examples. In the previous 2 examples, our constraint was based on the amount of materials we had to work with, in that case fencing. But in this case, we're trying to minimize the material. So now we ask ourselves, what is it that is constraining us in this problem? If you notice, the problem says the box has to have a very precise volume. That means the volume is constrained in this case. So we write down the equation of the volume and set it equal to our constraint, in this case 32,000 cubic centimeters. So now we have a problem. If you notice, we have to optimize one function and we have one constraint. But there are 3 variables, which means we won't be able to get rid of 2 of those variables with what we're given. Let's look more carefully at the statement to see if there's something we missed. The statement says that the box should have a square bottom. That means the length and the width are actually the same. If we had caught it earlier, we could have compensated for it in a couple ways. We could have started the whole problem with only 2 variables. Instead of length and width on the base, we could have just put length and length, or x and x if we didn't want to confuse ourselves. Alternatively, you can think of the box having a square bottom as a second constraint, and we could have listed it as another constraint. All of these ways of thinking are equally valid, so it's up to you to figure out how your brain likes to think about them. I decided to work it out in this way in the video in order to show you the kind of thought process you should have if you ever feel stuck. So now we'll use the fact that L equals W and change both our optimization function and our constraint to reflect that. After this work, our problem finally has the form of one function to optimize in 2 variables and one constraint in 2 variables. So we can now proceed as we have before. We use our constraint to solve for one variable in terms of the other. Then we will substitute it into our surface area function to finally have a function of one variable. In this problem, it would be wiser to solve for h in terms of w than the other way around. Notice that if we were to solve for w in terms of h, we would get w equals 160 root 2 over the square root of h. If we were to plug that into our original formula, we'd get a function that has several square roots, which are much less pleasant to derive and would just make all of our symbol manipulation more tricky. So instead, let's solve for h in terms of w. So now we substitute h equals 32,000 over w squared into our formula and get the area as a function of only w. So we now turn our attention to the domain of our function. Unlike the previous two examples, our domain is actually quite large. The width can actually be any number between 0 and infinity, not including 0. If you look back at our constraint, the smaller the value of w, the larger the value of h. But it doesn't actually exclude very small values of w, it just makes h very large. We will see shortly how we get around the fact that our domain is not a closed interval. So at this point, we have a function, we have its domain, so we know exactly what to do. We start out by finding the critical points. In this case, a prime will only be 0 if w equals 40. Notice that a prime will not exist when w equals 0, but that's not in the domain, so it's not actually a critical point. So this is the step that differs from a lot of what we did in 4.1. Since we have no endpoints to plug in, we need to do something more sophisticated in order to figure out if our critical point is truly an absolute minimum. We'll start by making sure that the area has a local minimum at w equals 40. In this solution, I've chosen to use the second derivative test, but you could have just as easily used the first derivative test, if you prefer. But this alone does not prove that our area function has an absolute minimum at w equals 40. To do this, we will use a second fact. Notice that for any value of w that is positive, the function has to be concave up because the second derivative is positive. This tells us that there can only be one minimum, hence what we have is actually an absolute minimum. This final step may seem a little bit cumbersome, because in general, if these problems were written correctly, the lone critical point should be the absolute minimum. But real life isn't as nice as these problems, so it's a good idea to get into the habit to confirm that what you got, whether it was by hand or with a computer, is actually what you were looking for. Now that we've found the location of the absolute minimum value, we turn our attention to actually answering the question we were asked. Since the question originally was asking us to find the dimensions of the box with minimal area, we need to find the height, so we plug in our value of w equals 40 into our equation for h, and then we finally state the answer to the question. Now let's turn our attention to another example that is very similar to the one we just did. There will be a step to the solution of this example that is slightly different than the last example. Because of the similarities, I will go quickly through many of the steps, slowing down for the parts that are different. So I recommend you all pause this video now and try this problem for yourself. Okay, so first things first, we should figure out what function we are trying to optimize. Reading the problem, we realize that we need to minimize the cost of the materials to make this box. This is the main difference between this problem and the previous examples. In all the problems we've done, both the functions we've been trying to optimize and the constraints were geometric in nature. The formulas we used, though often modified, were basically formulas we learned back in geometry. In this problem, however, we are trying to optimize the cost of making our box. This acts sort of like the surface area of the box, but it's different in that different sides of the box cost different amounts of money to make. So in some sense, we are trying to optimize some sort of weighted surface area. But this means we're going to have to come up with the function we want to optimize ourselves. So I'm going to break down this process into its individual parts. From the question, we see that there are two types of materials we need to use. Specifically, material for the base of the box will cost more than material for the other four sides. Since the base is a rectangle, we know its area is L times W. Since the box has no top, we know that there is only one base. The material for the base will cost us $10 per square meter. So the total cost to make the base of the box will be $10 times LW. Now we will deal with building the sides. The material we're going to use to build the sides costs $6 per square meter. Since all four sides cost the same amount, we will deal with them together. First of all, notice that we have two different kinds of sides. There are two sides whose area is length times height, and two sides whose area is width times height. So the total area of the sides is 2 length times height plus 2 width times height. So the total cost of making the sides is 6 times that quantity. Adding the cost of the two, we can finally derive our cost function. This time, since we read the problem carefully, we realized that the length has to be twice the width, or in other words, L has to equal 2W. So we'll make the substitution into our cost function now. So now we have to deal with our constraint. We see that we need to make sure the box has a volume of 10 cubic meters. And so that means the length times the width times the height must be equal to 10. But again, we know the length is equal to twice the width, so in reality, we get that twice the width squared times the height equals 10. So at this point, it's roughly the same as the problem we've already done. We're going to solve for h because we don't want to have to take square roots. Then we're going to plug in h equals 5 over w squared into our cost function to reduce the cost into a one variable function. Just like before, the domain for w is 0 to infinity. To make this solution a little different, I want to point out that, in order to make this solution a little different than the last, I'll start by pointing out that if w approaches either 0 from the right or infinity, our cost goes to infinity. Now we find the critical points in the same way as before. We see that the cube root of 9/2 is a critical point. And just like before, even though the derivative does not exist at w equals 0, it's not a critical point because it's not in the domain. Finally, we should verify that our critical point actually constitutes the absolute minimum. You can use the second derivative test exactly like in the previous example. You can use the first derivative test by showing it's decreasing before the critical point and increasing after the critical point. But instead, let me argue it a different way, just to show you the variety of reasons why this must be an absolute minimum. We know our function is going to infinity as the width approaches 0 from the right, and we know it's going to infinity as the width goes to infinity. That means if we take a closed interval where the left endpoint is very near 0, let's say 10 to the negative 10 billion, and the right endpoint is very, very large, let's say 10 to the 10 billion, we know our function will be very large at the endpoints. Thus, the absolute minimum will have to occur at the only critical point. And since our function goes to infinity outside of that closed interval, we know that must be the absolute minimum on the entire interval 0 to infinity. Now all we have to do is answer the question we were asked. If you look back, it asks us to find the cost of the cheapest container. So unlike the last time, we don't actually have to find the height or the length. We simply plug in the value for w we found, which is the cube root of 9 over 2, and the output it gives must be our minimum cost. Since the answer is in dollars, we can approximate it without losing very much information. Our answer is roughly $163.54. Well, that does it for this section. I hope it gives you some appreciation for all the stuff we've learned in Chapter 4. I highly recommend you look for more examples either in our book or other books or online, because these problems can be very involved, and seeing these techniques used in different settings can really help you master the topics. Well, I'll see you all in the next video. I hope you have a great day.